Thank you, Stefan. So I'm going to also say thank you for joining us here in the conference. I can see lots of new faces, which is always good, right? And also old ones, which are also good. And so yes, I don't know, 30 minutes. I'm going to try to keep that. And since last year, we are using the conference in order to present the new feature of the versions we are releasing. And this year, so this is BayesiaLab 8. You can see here the 6th topic I'm going to talk about. And the first thing we have done is to update the splash screen, right? So this is a huge improvement, right? So it was a splash screen we had designed in 2001. So after 17 years, now we have a brand new one, right? So for welcoming you when you start BayesiaLab. So this is not the main one, obviously. And we have worked a lot also on the user interface. You're going to see that we have lots of new features there. We are going to talk about some new features on the machine learning field, Bayesian updating field. So it's also learning, but by using the Bayes theorem. Then some features about segment analysis, and I will let Young present some examples with that. We are going to talk about the web simulator that we have updated a lot. And the very last feature is just a small technical thing, but very useful that you're going to see at the end of the presentation. Let's start with the user interface. Now, when you run BayesiaLab, you are welcome with a startup page. So this is almost the same thing as the splash screen. We had an investor in 2001 that was just saying, hey, when you run BayesiaLab, you are welcome with a dark or blue screen without anything. It would be good to have something. So now, after 17 years, we have something too, right? So you have here on the top icon for creating a network, opening a network, and also learning from data. And then the 6 other spaces are for the recent Bayesian network you have open, right? Then we have also updated all the icons, right? So you have in the toolbar, you can see brand new icons. I guess you recognize some are brand new. And there is also an option that allows you to decide which size of the icon you want. So here you can see the biggest one, right? So for me, I think it's too big, but for this presentation, I thought it was good. So you can go from small, medium to large. Let's focus a little bit on the new icons, just to get you familiarized with that. So here you have an icon for representing what is a default choice. This is for the structural coefficient. This is for the preferences, where you can really set up your BayesiaLab. This is for removing all the evidence in the monitors. So this is when you do brainstorming with a group of experts, with Beaky, for example. So this is an icon you're going to have on the nodes that have different probability distribution corresponding to all the expert knowledge. You have this one for when you click on it, hovering over the object in order to have some information. You have the smooth probability estimation, stratification, evidence scenario file. So this one is new. This is in order to indicate that the node is not observable. So before it was just slightly shaded. Now you have this icon on the node to know that you're not going to be able to observe this node. And this one is for being able to observe a node when it's not observable, and so on. You have this one for the search function, right? And I'm going to just focus a little bit on a new feature for this search function. Now you can also search for actions, right? Because given the number of features that are now available in BayesiaLab, sometimes it's kind of difficult to find where is the feature in the menus, right? Even me, I'm lost because I'm so used to use my shortcuts that I don't remember where are the features. So now you can just search. Here I just enter COEF, and I have all the features, all the functions that contains COEF in their name. And then you can select, by clicking this icon, you will run directly this feature, right? And then because it's Halloween, we have also 2 new icons. So this one for indicating that your node is hidden. It's a little ghost, right? And this is one of my favorites. This is what I call the screamer. This is for indicating that you have classes, right? So we already had this one before, but it's slightly better now. So this was for the icon. And I think the main improvement is in the appearance of the node, right? So I guess that you remember that before, this was the way to represent our node, right? So we are using that since 20 years, this little blue node called sometimes bubble, right? So now the technical name is disk, right? So obviously we still can have images instead of just the disk. And there is a new rendering function that allows you to directly specify what you want to have, what is the font size, color, and so on, if you want to crop the image, and little technical things like that. And there is another one now that we can call static, which is called a badge, right? So by default, if you create a node and you set a badge, you will have this little node. You can also obviously associate images with these badges, right? And then choose where you're going to have the label. And you have also rendering properties like that to choose the color of the background, the color of the font, where you're going to put the label if you want to have different corner style and so on. So lots of degrees of freedom for making your presentation nice. And we have 3 other appearance nodes, but that are dynamic, right? So the first one is what we call a monitor. So this is what you had before in the monitor pane on the right side of BayesiaLab. Now you can directly have the monitor instead of the node, right? So you can have a graph with the monitor, so you're going to see the distribution, obviously. You can also define what color you want for the label, define if you want to have a long name, a comment, so what you had before too. And it's also a way to set evidence. So you can see what is the result of the inference, but you can also obviously interact with the monitor, and then it's very useful when you have, obviously you cannot use that when you have 100 nodes, but when it's a network that has a few nodes, it's very cool for presenting and for interacting because you really see the path of the information. Right? And again, a large set of options. The second dynamic one is what we call a gauge, right? So it's also, obviously it's better to use that when you have a numerical variable, right? So here you have an example of a positive gauge. This one is a negative one. You can choose where is the red, where is the green, associate images. And you can also set numerical evidence with that. So you can really click here and choose the value you want to set, right? And same thing for the rendering properties. And the last one is a bar, so also for numerical values. And it's slightly smaller, so sometimes it's better to use that. You can see here the icon for the not observable nodes. And you can also set evidence on these bars, right? And same rendering function. So these are the 5 types of appearance you can choose for your nodes, right? And so given all these degrees of freedom now, you can also define what you want in the preferences, right? So you can define what is a default node renderer. So are you keeping the disk, or are you going to switch and use the bar or the gauge or whatever? Then you can also define, because given that the size can be big, we have defined a minimum size, right? So you have here a way to set what are your preferences for the small size of your component. And given that we have so many degrees of freedom too, it's really cool to be able to copy and paste the format, because you can spend some time setting your monitor, your gauge, and bar. And if you have to do that for 20 nodes, it can be tedious. So with that now, you can make a copy of your node and then paste the format to a set of nodes or even arcs. Right? And this also features that is quite obvious, but now you can also move the nodes with the keyboard. I don't know why we did not have that before, but now you can really align all your objects in your graph. So this was for the user interface. Now let's switch to machine learning. And here we just work on 2 categories. So the first one is discretization, and the second one, unsupervised structural learning. So for discretization, I guess you know how I'm presenting them since a few years now. So we have the continuous node that is hidden, as you can see with the ghost here. So we don't have it directly in BayesiaLab, and we have to create a discrete representation of this node, right? So this is what I call the discrete clone. So we have then, it's like creating a hidden variable, a latent one, and then we have to choose how many states we are going to have for this node and so on. So what we did, first to create a heuristic in order to help you find what was the optimal number of bins given the size of your data set, because it's really a choice that is not that easy. So here, let's suppose we have these two parents and a child, we have a data set. It's obviously not the same thing if you choose to have 2 bins per node than 5, right? So in one case you have 8 cells, in the other one you have 125 cells. And then the more cells you have, the more data you need to populate this table to be able to have a fine priority estimation of these, right? So here there is a heuristic we are using since a few years, which is, the one used in the statistical community to have 5 samples per parameter, except that we don't have any parameter in the Bayesian network. So the idea is to, at the end of the day, try to have 5 samples per cell in the biggest priority table you have in your network. So if you can use this heuristic reverse in order to define the number of bins you can have, right? So this is what we came up with. So this is an equation that is using the fact that we are looking for 2 parents per node, and then we are using the size of your data set, n, that we know, and then define automatically the optimal number of bins. Not really optimal, but a good choice, right? So depending on the size of your data set, you will automatically, when you open the data wizard, you are going to have the number suggested by this heuristic, right? What we did also in this the same kind of idea is to try to help you find what is the best number of bins, is to create a new algorithm. So you remember we have added R-squared genopt a few years ago. Let me kill this. And we have just created a new version, R-squared genopt star. We are not lacking of imagination, as you can see. And so this is a pure extension of this algorithm, where, so if you remember, this algorithm is just using genetic algorithm for finding the best discretization in terms of R-square. So we are trying to maximize the R-square between the hidden continuous node and the discrete node we are creating, right? So it's a best univariate discretization algorithm we have. But this one now is using an MDL score that we have created on purpose for finding the optimal number of bins given the amount of data you have, right? So you can use R-squared genopt star with 10 bins, and if there is not enough data, it will give you 2 or 3 or 4. It will decide the optimal number for you, right? Now for unsupervised learning, so this is, I don't know if you are familiar with my way to present that. I am a particle guy, so I'm talking a lot of particles, and here a particle is one Bayesian network, right? So the idea of learning, trying to find the optimal Bayesian network, is to explore the space of all the candidates, right? All the possible Bayesian networks. So there are a super exponential number of solutions. So we have to use heuristic search for that. So here you see this is like we are starting with this red solution and then optimizing the MDL score for, at the end of the day, finding the yellow solution that is the best one, at least in terms of MDL, if we use the greedy search, right? So we have, obviously, we are using taboo search, which is a kind of extension of the greedy search, where instead of stopping here, we are still trying to escape from some local minima, because with the greedy search, we are always choosing the operators that allows you to decrease the most the MDL score. So with taboo, when we are in a local optima, we are choosing the operator that's the best one, even though it's increasing the score, right? And with that, we are hoping that we will be able to escape from some local minima. So this is exactly what I'm representing here. So this taboo search, we have, because in the training session I was doing during the last few years, I was always telling you, you have to use EQ, and then on top of EQ, use taboo, and then same thing for maximum weight spanning tree. So now we have an option for that. You just check post-processing with taboo, and you are going to have the taboo search on top of the result of your current algorithm, right? So this will help you escape from local minima. And based on that too, I guess you know the EQ algorithm that we have. So this one is searching, so the space here, one particle is not a Bayesian network anymore. It's an essential graph, you know. It's a partially directed acyclic graph. So here you have a Bayesian network. Here you have this essential graph, so where you have a mix between edges and arc. So we have an edge when we cannot decide if it's AB or BA, when it's equivalent from a probabilistic point of view. So this algorithm was searching in this space, but at the end of the day, it was a greedy search too. So what we did, we just increased the capability of this algorithm by using a taboo search in this space, right? So I'm not sure it's 100% efficient right now. We still have to work a little bit on it, but we are close. Right? Now let's switch to something really interesting, Bayesian updating. So the idea here is to update the probability table of your network by using Bayesian inference. Right? So I guess perhaps you are familiar with the hyperparameter updating function we had already, but now we have also what we call the parameter updating. And I have to introduce first my particles, right? But now a particle is not a Bayesian network. A particle is one observation of your domain. So if you are in the medical field, it will be one patient. If you are for P&G, it would be one customer. It's really one observation of your domain, right? So you have this cloud of particles, and there are two scenarios. Either you don't have data, but you have expert knowledge. So these guys, our friend from Firmenich here, they have knowledge, right? So they have in their mind lots of particles. It's not structured, but they have particles. So either they had this particle because they did some experiment, but they also went to training. They are reading some scientific papers and so on. So in this paper, this is the description of particles, right? But not structure. So the idea when you have only this guy for building your network, you have to do brainstorming in order to try to extract this particle for building your Bayesian network, right? And the other scenario is that you have a structured data set, right? So you have either a sensor, you have a database, you have some things that for each particle, you know exactly, you can measure all the dimension of these particles that I have represented here with these nodes, right? So we have these two scenarios. And what we do when we use data, so structured data, so the right side of my slide before, we are using the maximum likelihood estimation for estimating the probabilities. So it's a purely frequentist approach here. We are just counting. If we want to estimate the probability of y given x, we just have to count how many particles we have with xi, yi divided by the number of particles with xi, right? So highly frequentist, but quite dangerous, as usual. Because if you don't have any observation in one or two cells, you are going to conclude that this is impossible. And then, if you don't have enough data, and if it's indeed not impossible, for the cases that you will encounter on these cells, you will not be able to use your network, right? So to overcome this problem, we can have a more Bayesian approach by using Dirichlet priors, right? And so the idea is to still use your data, obviously, but then also expert knowledge, right? So we can imagine that we have these experts that are designing a Bayesian network that represent the particles they have in mind, right? And then we have two sources of particles, and we are mixing the one that we have in the structured data set with the virtual one created by these guys, right? And then at the end of the day, it's like the maximum likelihood estimation, but with two different pieces of sources of particles, right? So this is what we have before version 8. We had two ways to use this Bayesian estimation. The first one was, you remember perhaps the smooth probability estimation, which is indeed something that is more or less mandatory to use, right? So where you are starting with a fully unconnected network. So your expert knowledge is that everything is independent and uniformly distributed, right? So with that, if you create a particle with that, you are just specifying that everything is possible. So if you, even though you have never seen something, it will not be zero, right? So then you can be confident that you will always be able to use your expert system. And the second way was to design a Bayesian network prior to learning and define an equivalent sample size to generate particles by using this Bayesian network. So these were the two ways to create that before. So what we had added just last month was to be able to take into account, to create particles manually. So now you can use your Bayesian network, set evidence in the monitors, right? And then generate a particle with this Bayesian network and this set of evidence. So it can be a complete observation with hard evidence, it can be incomplete, it can be with soft evidence, with likelihood, with probabilities, it can be numerical evidence, it can be fixed, not fixed. You have all the degrees of freedom here, right? And then we are creating one particle with that, mixing it with, or this one. You have, so this is the particle you are creating, the network you have right now, and then we are mixing the particle we have here with the Bayesian network we have already, time the number of the prior weight that we call here prior weight, times the discount, because you can also forget the old particles if you want. So this is just here, what we call the first way to use that is what we call the sequential updating. So you have first to define what is the prior weight for each node, right? So if you do that, so you can do that obviously via the edit node, or node editor, and then set your prior weight for each node, for each conditional distribution, if you will. Or you can select all the nodes, and so, for example, here I set 100, so it was 100 for this one, and here it's obviously spread uniformly in the conditional probability table. So this is when you do that in modeling. But if you do the same thing in validation, then we can already use the joint probability distribution to dispatch this probability by taking into account the probabilities, right? So we are dispatching the weight here based on the probability that this configuration occurs. And then, once you have that, you can define what is the source of your evidence. Are you going to set evidence in your monitors? Or are you going to load this from your evidence scenario file? Or are you going to directly use what you have in the data set? And then you can also set use the client priors if you already set that manually, compute the prior from the data, or set here, initialize your prior by using the joint. And then you just have to use this tool for updating your probabilities, right? So this was a sequential one, and we also have created an iterative batch updating, where instead of doing that for one particle, we are taking into account a set of observations. So either coming from an evidence scenario file or your data set. And then we have, obviously, the Bayesian network we had before, and mixing the particles. But here it's not one by one, it's really in batch. So if you have 100 observations here, we are going to use the 100 particles here for creating this O of X and Y. Okay? And then you click on this icon because it's an iterative process. So if you have missing values, then it will be like expectation maximization. Right? And now that we have this tool, it's quite interesting because it opens lots of doors, as usual. And I can see Mike now. You remember the tool you wanted for the evidence instantiation, so that we did for you guys. It was not perfect. I don't know if you remember, there was a little problem. So let's suppose that you want to create a network and change the marginal distribution of your network, right? So either because you want to create a new scenario or because it does not fit exactly what you know from the marginal point of view. So here I have a little network with, I set evidence here, and the joint is 29% given my Bayesian network and this set of evidence. With the evidence instantiation tool, we had a perfect result for the parent, but given that we had evidence on the child, here, with the d-separation, these two guys are marginally independent, but conditionally dependent. So because of that, we were not able to have the perfect match with this distribution. As you can see, it's not exactly the same. It was not a big deal, but it was not so nice. Now, with the evidence instantiation, with the evidence instantiation, with the parameter updating, we have the perfect solution, right? We just have to use EM, the one I was describing before. We can set a discount of 0 just to discard. We just use the structure. We are not using any equivalent number here. And then with EM, we have the perfect match. Right? And we can also, and indeed this was the reason why we went there, we can now also use prior in the expectation maximization algorithm we have. Because I don't know if you ever tried, when you use parameter estimation in the learning menu, if you have some hidden node, we are using the pure 100% machine learning approach. So we are really just using the data. So we were just randomly generating distribution, and then we were using EM on that. But the problem is that if you have some expert knowledge, as in this case, my hidden variable is this one, and my expert gave me this table, where there is a rule. He knows that, right? He does not know lots of things, but something he knows for sure. So with our parameter estimation, the previous one, the first thing we were doing was just forgetting everything, right? So it was kind of not so cool. So now, with that, we are taking into account the prior knowledge, and we have an expectation maximization that uses your expert knowledge without discarding everything. I did not spend time to build another slide because we can also replace the hyperparameter updating with this one too, but it's not really the day for that. So now to come back to our classical hyperparameter updating, I don't know if you remember how this is working. This is when you have, so a Bayesian network is a non-parametric model. However, we can have a kind of parametric model when we are using an equation, or not, but when we are usually using an equation in this node, and then we have the hyperparameter of the equation directly represented with nodes, right? So these are the hyperparameters, and the idea is to use evidence we have on this one to update via Bayesian inference our uncertainty on the hyperparameters. Right? So before version 8, you just had you had to use either an evidence scenario file or a database. So now, in order to have the same kind of tool as the parameter updating, you can also manually set evidence, right? And we also added this edit hyperparameters that allows you to define directly via this tool what are the hyperparameters instead of using my screamer, right? Now let's switch to segment analysis. And I will let Young talk about that in a few minutes, because this is a set of features that have been designed for PNG. So the idea of this feature is these features is to analyze sub-data sets, right? So when you have segments or legs, right? So the first tool is called the profile. So it allows you to compare the mean value of your drivers or your variable on different subset of data. So now you have this radar chart that gives you the mean value for all the segments. And there is an option here to carry out a null value assessment. So the idea is to just know, are the mean values significantly different, right? So we have implemented, well, not so complex, the t-test, right? And the Bayesian estimation called BEST, right? So it comes from Kruschke. And this one, there is a direct link with my previous slide with hyperparameter updating, because this is hyperparameter updating, right? So we have the samples for the segment 1, we have the samples for the segment 2, and we are assuming that they are coming from a student distribution with a standard deviation and mean value, and they are sharing the same parameter here, right? And then we compute the effect, and we can via Monte Carlo simulation, because here it's a Bayesian network with continuous nodes, so we have to use approximate inference and not exact inference. So we are able then to know or to estimate if it's significantly different or not. And at the end of the day, the result you have are these little square, right? Perhaps we have to change the color, who knows? So when it's a dark blue one, this means that this is significantly different from the Bayesian point of view. When it's light blue, it's from the frequentist one. Then we have the second one is called the impact on target. So here you compare the mean value of your segment with a selected benchmark that can be either another segment or the entire data set. And we compare that by comparing the mean values, obviously, time the effect of the node. And the effect can be either the total effect, standardized or not, or the direct effect, standardized or not. And then you have this kind of graph. So when it's green, your segments perform better than the other one. When it's red, it's worse. And same thing, you can also have the Bayesian and frequentist test for knowing if it's significantly different or not. And the last one is just a small update of our multi-quadrant, where you can check here show landscape that will allow you to really have access to the range of the values. So we already had that before, but it was a kind of cloud of dots. So now you have everything on the scale of the y-axis here that correspond to the overall, right, to the entire data set. And then now let's talk about the web simulator. So I guess you are familiar with this tool that allows you to share your network with your peers without having them to use BayesiaLab. So here we also change the startup page if you want. So we have a very nice welcoming page now. So we were just thinking about Netflix, how good it is. So we say, okay, perhaps we can do something like that. So we have here the recent addition. Then you have the most popular one. And here the entire set of models with a preview. And we also added here some fields. So you can define the field of study for your network and also the type of analysis, right? So this way, if you just want to see the networks that are in the medical field, you select medical, and then you are going to have only the networks that belong to this field. And within BayesiaLab, what we have done was to really try to bring everything within BayesiaLab without having to edit your simulator in the web interface, right? So in this web simulator editor, there is a first tab for defining your simulator. So you can define, obviously, the name, the title, you can define the author. Here, this is for the field of study and type of analysis, the description. And here you have a description, a picture. You can take a snapshot of your network. This will allow you to have, when you have the preview, to have your network directly there. You can choose, obviously, your logo, URL, and so on. And here, this is just some snapshot of the web simulator. So this is the name of the model. Then you have the title of the model. Here you have, when you press on the icon or when you hover over it, you are going to have the description of this model. And here, by clicking on this little eye, you have the preview of your model, right? And this is where you can choose the field of study and the type of analysis. And when you hover over a model, you have the description automatically popping up. Then you have the second tab. This is for defining your input. So you can just drag and drop the nodes here. And then when you drag and drop a node here, you are going to prompt to select what type of object you are going to use for that. Then you can here define all the settings you want with the size of the image, the font, and all this stuff. And same thing for the output, right? So drag and drop. You can also use that as an output with the join, the log loss, and the global utility. You can define the same thing with the image, the format for the output, and all this little stuff. And then you have this function. So you can directly click on preview, and this will allow you to have a preview of your simulator without having to publish it directly, right? So This way you can quickly see if it fits what you want, right? And then when you go to the Web Simulator website, you just have to, it's just 3 or 4 clicks and everything is published, right? And the last one, as I said, it's a more complex one. This is inactivity timeout. So this is meant for those who are using tokens, right, and who forgot to switch off, right? So it's we have lots of customers that are just, this is like as the light, you know, you go off your office and you forgot to switch off your BayesiaLab token. So this token is not available for the other one, or even worse, if it's an elastic pricing, you are charged for that, right? So now you can define an inactivity timeout. By default, it's 30 minutes. You can set the delay you want, and then when we reach this delay, BayesiaLab will drop the token. Okay? So that's it.